Well, thank you very much. I'm very pleased and honored to be here on this very special occasion for Franck. I think the first day Pierre-Louis said it was one of the first, he had the oldest, yeah, almost the first, because I think I could claim having an earlier acquaintance with you, and probably Thierry is more senior, far, because you met in the lycée, yes, in Marseille. So I mean, I cannot compete, obviously. Yes. Okay, so I'm very happy for this occasion, 60th birthday, and for all you've brought to, to this place, and of course to Sergi and what you've done in the French math community, working in PDEs. Okay, very good. So that being said, I'm going to present a joint work with Cyril Imbert from Ecole Normale and Alexis Vasseur from University of Texas at Austin about the Landau equation. So, all right, so where are we? Okay, so what is the Landau equation? So the Landau equation is the it's a collisional model. It's a collisional kinetic model for the charged particles, electrons, say in a plasma, interacting via a Coulomb repulsive force, right? So so it's not going to be mean field like in the talk of Sylvia. It's really a collisional model, and in that case, it's been known for quite a long time that the Boltzmann equation does not make sense for Coulomb interaction because of grazing collisions, among other things. And you have to replace the Boltzmann equation by the Boltzmann collision integral by this object here, which is the Landau collision integral, and which I'm going to describe now. So the Landau equation written here is in the space homogeneous case. Normally the unknown is a function f of t, x, and v, which is a density of particles which at time t are at position x with velocity v. Right, so here I'm going to consider the case where there's no x dependence in this distribution function. So f is going to be a non-negative function, and it satisfies this equation here, written in this form. Right, so del t of f is equal to the divergence in v at the integral of a of v minus w, the collision kernel resulting from the Coulomb interaction, del v minus del w of f of tv, f of tw, dw. All right, so here a of z is up to a constant, 1 over 8 pi, the Hessian of the norm of z, right? So you can write it in this way. So 1 over 8 pi, the norm of z times the projection, the orthogonal projection on the orthogonal to the line spanned by z. All right, so obviously you can write this equation here in non-conservative form, in which case it appears in this way. So you have del f by del t is equal to the trace of some diffusion matrix, which is obtained by taking the convolution of f in velocity with this kernel A. So you apply this matrix to the Hessian of f in V, right? And there's an extra term that pops out, which is special to the Coulomb case, which is f of tv to the squared. There's, the coefficient in front is 1 if you put a 1 over 8 pi here. All right, so the open question for this problem, of course also for the more general problem where you have the x dependence, but certainly for this problem here, is whether you have global existence or of classical solutions or finite time blow up for the Cauchy problem if you start with an initial data f in at t equals 0. Obviously, there's something I didn't mention here, but you want your initial data to decay in v at infinity. Specifically, you want f of t and v to be integrable in velocity. Otherwise, the blow-up problem would be obvious. You take a function that's independent of velocity. But functions that are independent of velocities are not very interesting in kinetic theory because they don't have finite mass. Okay? All right, so if you look at this form of the equation here, it's reminiscent of an equation which Franck and Atem like very much. I'm going to, but I mean, these are the experts. I know almost nothing about this equation here. But it's a semilinear heat equation. Well, you can think of comparing the Landau equation to this equation here, delta u equals Laplacian u plus positive coefficient alpha u squared. All right, so then in that case, you know there is finite time blow up for positive solutions of this equation here, and I can't resist the pleasure of quoting a paper by Stanley Kaplan, which is exactly 60 years. It's slightly younger than us, right? 63, paper appeared by 63 in CPAM. And the idea is known, I suppose, to most people in this room, right? I mean, you take the average, what you do is I mean, it's going to be, again, a Riccati equation that's going to appear. But here, you take the average of the solution with respect to the ground state of the Laplacian Dirichlet in a ball, right? So here, lambda naught is really the fundamental, I mean, the lowest eigenvalue. Phi is positive on the ball, equal to 0 on the boundary. Minus Laplacian phi equals lambda naught times phi. You look at this quantity here, you average the solution u of t and x of your semilinear equation here with respect to this phi in the ball. And well, you do a little computation, Green's formula, and you end up with an inequality of Riccati type for L. And this tells you that if L initially is large enough, then you have a blow up in finite time. Okay? All right. Now, there's a difference, of course, between this model here and the Landau equation, which is that suppose that you have f, which starts increasing at some point, then presumably this will feed the diffusion coefficient here. And so this is, of course, at variance with the semilinear heat equation, which I showed you before. And the fact that f is going to grow, you expect that it would sort of tame the growth itself. So there is probably an equilibrium between this term here and this f squared there, which has to be discovered. I mean, there's a fight between these two terms. This one promotes blow up, but the fact that this one increases as f increases is supposed to prevent blow up, right? So there's a variant of the Landau equation for people who don't like this matrix A, which goes by the name of the isotropic Landau equation, but I don't think it's a physical model, right? But nevertheless, it's a toy model, which is useful to understand what's going on, where you replace this diffusion, which is a convolution of f, with something that looks like the Coulomb potential, except it's a Coulomb potential times an orthogonal projection in the ortho complement of z. So you replace it by this equation here. So del t of u equals minus Laplacian to the minus 1 of u times Laplacian u plus some coefficient alpha u squared. And here you set alpha between 0 and 1, say. So this is a model that's been considered by Krieger and Strain, Grassmann, and later by Maria Pia Gualdani and Nestor Guillen. Well, and they managed to prove for this model the global existence of non-increasing and radially symmetric solutions for alpha equals 1, right? So this is an equation that would be sort of the closest approximation to the Landau equation. But this one has a stronger diffusion, so it's not completely conclusive. And on the other hand, there's a feature which this equation doesn't have, which is that for this equation, for the Landau equation has equilibria, Gaussian distributions, our equilibrium solution for this equation. This one doesn't have equilibria, right? So it's a very different equation, in some sense. Okay, speaking of equilibria, let me say a few words about the formal properties of this Landau equation. So you have conservation of mass. Well, that's obvious because it's a divergence of something. Momentum and energy. Well, momentum is not very hard either. Energy really uses this projection pi of z that appears in this kernel A. And this is the reason why this isotropic Landau equation doesn't conserve energy and therefore doesn't have equilibrium, right? Okay, but here you have conservation of mass, momentum, and energy. So these integrals of f times 1v and norm of v squared are going to be constant in time. There's also a variant of what's known in the Boltzmann case of the H theorem. So assuming that f of t and v is a classical solution, positive almost everywhere, so you can prove that the time derivative of the integral of f log of f dv is a non-positive quantity. So specifically, it's equal to minus this double integral here, right? So it's a non-local term. So you have this electrostatic interaction here, and we have our friend the projection on the orthogonal of v minus w of del v of log f minus del w of log f. Right, so you see here that exactly when this is equal to 0, it means that del v of log f is going to be a linear combination of 1 and v. It tells you that the log of f is a linear combination of 1, v, and norm of v to the square, and that's where you find these Gaussian equilibria. Okay? Good. So now, if you look at this dissipation term here, it's a bit unpleasant because this double integral and also the fact that you have a derivative in the direction v minus w. There is, however, a very nice, quite recent result by De Villet. And this result connects this dissipation term to something that's known as the Fisher information, which is the L2 norm of the gradient of the square root of f. So here's the inequality, right? I mean, it's a functional inequality. It doesn't have anything to do with the solutions of the Landau equation, right? So suppose you take any function that's non-negative, which is L1, L12 of R3. Oh, by the way, I'm going to use systematically this notation here. So L1p means, or LPQ, right here LPK, means that I'm in LP for the measure 1 plus norm of v to the k dv. Okay? So I'm going to systematically use this notation for the weights. All right, so you take f, which has finite mass and energy, and with an integrable f of f log f, then you can show that up to a constant that depends essentially on the conserved quantities, you know, the mass, the momentum, the energy, and the entropy, the h function. Then this double integral that appears as the dissipation term in the Landau equation is bounded below by the Fisher information of f divided by a weight that decays like v to the cube at infinity, right? So apart from this weight, this is really the Fisher information. Now, if you look at this, this tells you so it tells you already something. Well, I don't know if it's maybe surprising or not. I don't know. Which, in terms of Lebesgue exponents, it puts the Landau equation in the same league, in the same class with the 3D Navier-Stokes equation, in the sense that we know that for Navier-Stokes, for 3D Navier-Stokes, the velocity field is L infinity in time with values in L2 in x, in low-ray solutions, right? And grad u is L2 in t and x. Well, now, here, it's going to be roughly the same thing apart from these weights decaying at infinity due to the decay, the Coulomb potential at infinity. So for Landau, the dictionary is like u is going to look like square root of f. So here, f we know is in L infinity in time with values in L1 with the weight 1 plus v squared. So square root of f is L infinity in time L22 in v. And what this inequality here tells you is that del v of square root f is L2 in time and velocity. Unfortunately, there is this weight v to the minus 3. But apart from this, speaking of the exponents, you're roughly speaking in the same, you have the same exponents. Okay? Okay, so you can expect some similar properties to some extent. Okay? All right, so so you have this diffusion matrix, which is singular at the origin. Let's truncate it. So I'm going to use a truncation of this collision kernel in the following way. I truncate it near the origin by some cutoff function, right, like this. And there is the following ellipticity bound, which uses the H theorem, right, which uses the fact that f log f is in L1. So in other words, f cannot concentrate on sets of 0 measures, and as a result, it's impossible that f would concentrate on those lines where A is degenerate as a matrix, right? As a result, what you can prove is that if you consider an f which is non-negative, which has given mass, say oscillating between two, I mean the mass is constant of course, but suppose that it's between two bounds, say m naught and capital M naught. Suppose that you have finite energy and finite entropy, then you can show that for delta, for all delta small enough, f convoluted with a delta is larger than some constant divided by 1 plus v to the cube. Right? So the fact that you have a degeneracy direction in A is not a problem because of the entropy. The f cannot concentrate on the bad directions. Good. So then with that, you can show rather simply that locally bounded Landau solutions are going to be regular. In fact, you don't need to prove regularity. You just need to prove the only thing that can go wrong is that there's a blow up in L infinity, if you want, right? If you control the solution in L infinity, then everything is going to be all right. And well, I mean, one argument, sort of formal argument to see that. I mean, okay, so let me introduce this notation for parabolic cylinders. QR of TV is going to be the parabolic cylinder terminating at t in time and centered at v and with radius r and size r squared in time. Okay, so then if f is non-negative and L infinity is some parabolic cylinder, then when you look at the diffusion of f, well, there's a piece that involves the truncated kernel, which is going to be nice anyway, because you get something which is going to be L infinity using the L1 bound of f. And there's a piece where you're going to use the local L infinity bound on your cylinder. Well, I mean, you have the A minus A delta, which is not going to be nice, but it's going to be localized. So essentially, you can prove in this way that this diffusion is going to be L infinity in a slightly smaller cylinder. Right? And with the ellipticity bound, you use, for instance, Krylov-Safonov to the non-conservative form of the Landau equation. Then immediately you get that f is going to be a Hölder on a smaller cylinder. And then f star alpha, the diffusion matrix, is going to be a Hölder itself. And then you can use Schauder to put yourself in C1 plus alpha over 2, 2 plus alpha in an even smaller cylinder. So in that case already here you reached classical solutions. Right? So the only thing that you have to worry about is whether things blow up in an infinity. Now, there's a very interesting conjecture by Louis Silvestre, which I think goes back to last year, or maybe the year before last year. So the paper appeared last year, so I don't know. I mean, I became aware of this last year. So there's a very interesting conjecture. I don't know if it's wrong or true. If it's true, of course, it settles the regularity problem in a very nice way. So Louis conjecture that local in time classical solutions of the Landau equation with finite mass, energy, and entropy, if they're initially in L infinity, satisfy this inequality here. So the L infinity norm of f at time t is less than or equal to something that Louis calls a magical constant times the L infinity norm of the initial data. So the magical constant, let me explain where it comes from, because it's an interesting it's an interesting idea. Okay, so as t tends to infinity, because I mentioned already equilibrium, you would expect that f of tv goes to a Gaussian centered at u with variance theta times identity and with density rho. And these rho, u, and theta can be computed in terms of the initial data by these formulas here, which are familiar to everyone working on the Boltzmann equation, conservation of mass, momentum, and energy, right? So it's the parameters of the relation between parameters and moments of Gaussians. And, well, at the end of the day, if you can, I mean, the conjecture of Louis says, well, the maximum amplification, which I'm going to observe in L infinity, is going to be the ratio of the L infinity norm of the final Gaussian, or the Maxwellian, the equilibrium, to the L infinity norm of the initial data, right? So, and if you, of course, I mean, this is a very wild conjecture, because in the evolution you have no idea what's going to happen. But at least you know the end, you know the beginning, you can compute the ratio, and then you have just this little variational problem that you have to solve. And indeed, because the so the thing is that in order to make that as large as possible, you want theta to be as small as possible, which means that you have to concentrate the mass near the origin. But if you want to do that with a fixed ceiling at 1, say, that tells you that you have to do that for the indicator of a ball. And if you do that for the indicator of a ball, you compute the numbers and you find the magical constant in this way. Voila. Yes.
Can you go back to this maximization problem? Why you impose this condition from the effort?
Why do I impose this? Well, I mean, these conditions you can sort of obtain them by scaling and translations, right?
Okay. Yes, but then it doesn't really fix the theta, right?
It doesn't fix the theta, of course. And that's, yeah, I mean, and so what I'm saying is that you have to you have to take theta in order to make this maximum. You have to take theta minimal, right? And then it means that you have to concentrate everything near 0. Okay? Satisfying these constraints, of course. And that gives you this. Okay. You're not convinced? Well, I mean, there's a little complication. I'm sorry? Oh, yeah, the conjecture is true. I'm not convinced at all. But I mean, this variational problem, that I know how to do it. The conjecture is a different story.
Okay, but I don't really understand the relation between the variational problem and the...
Well, I mean, the variational problem tells you that if there is a constant, the variational problem tells you where this constant comes from, right? I mean, it's, but it's a conjecture. I mean, that's what I'm saying.
So, am I understanding that you're not only maximizing over f, but also supremizing over rho and theta?
No, because if you know f, you know rho and theta.
Ah, you know rho and theta can be computed by. Okay,
yeah,
fine.
exactly. Right, so at the end of the day, it boils down to taking theta minimum, satisfying these constraints.
Okay, so they are all related somehow.
Yeah, exactly. Yeah, but the formula is given here. Okay, very good. So, well, I see that this conjecture attracts your interest and your attention.
A constant solution on some interval to Gaussian.
Yeah, exactly. And then you hope that nothing wrong happens in the middle.
This conjecture
I wouldn't put my head on the block, okay? But I'm a very cautious person. Okay, so that's a conjecture. Let's try to move to things which we know are true, which we know are false. Yeah, no, this one I'm going to tell you only, well, I hope only true things from now on. I mean, things which are verified. Yeah, so like, I mean, truth is usually less interesting than dreams, so, well, sometimes, well, who knows. Anyway, so now with my function chi, if you remember, there was this cutoff function, right? Like this, your favorite cutoff, say, between -1 and 1, say. Well, you introduce a truncation like this, truncation at large V. You introduce modifier, approximation of the identity here. You normalize the mass by this x. And with this, Villani constructed global weak solutions, a class of global weak solutions to the Landau equation, which he called H solutions, because this construction is based on the H theorem, this dissipation term which I showed you, right? And so Villani's approximation procedure is as follows. So what you do is you truncate your collision kernel the way I showed you before. So it's the same A delta as before. You chop out the thing near the origin, and you add some Fokker-Planck term in velocity like this, and you truncate your initial data at large V. You smooth it with the zeta delta, and because you want this solution to be positive and not only non-negative, you add beta for Gaussian here. All right. So with this, you can check that for any positive delta, this problem has a solution. And really, the thing is that as delta tends to 0, you can prove that this f delta converges to an object, which Cédric calls a H solution of the Boltzmann equation, which satisfies a certain number of properties. I'm not going to show you these properties because I'm going to need more properties, right? But these more properties are implied, these additional properties are implied by this construction, by the way the solution is built, right? I mean, it's like in the suitable solutions in the Caffarelli-Kohn-Nirenberg, they're obtained by the same approximation procedure as was used by Leray.
Maybe up to a subsequence or the whole sequence in the loop?
Oh yeah, no, up to you take a subsequence.
If the whole sequence converges, that's Planck solution. Huh?
No, subsequence. Sorry about that. Yeah, I mean, should have said. Yeah. So good point. Yeah. Yes. Yeah. You take limits along subsequences, then you have your H solutions. But in fact, I'm going to these H solutions. If you look at the definition, they might fail to satisfy some properties which I'm going to use, but which are satisfied by these limits obtained in this way, right? So let me call them Villani solutions for want of a better terminology. All right. So now, what do we know about these solutions? So if you take a Villani solution of Landau equation, to assume that initial data F initial is non-negative almost everywhere, and has finite mass, energy, and finite entropy. Then the first result, I mean, there are two results which are essentially the same result if you want, but I mean, the best result is in the case where F is radially symmetric. So in other words, if F depends only on the norm of the velocity field, then you can prove that F is going to be locally bounded everywhere except perhaps at the origin. Okay? So in particular, because of this local regularity which I told you before, then F is going to be a classical solution except perhaps at the origin. Okay. And same if F is axisymmetric, so in other words, if F is invariant by rotation around an axis, then F is going to be locally bounded except perhaps on the axis of symmetry. Okay? All right, so let me try to... So by the way, you see now how it connects to the case of the isotropic Landau equation, which I discussed in the result by Maria Pia Gualdani and Gillen, right? They consider the case of radial solutions decreasing in the norm of V. So here we don't have this assumption of decay or of monotonicity in the norm of V, but we don't control what's going on at the origin. So the only point that remains to be treated is the origin. Okay, so how do we do this? So there are not so many a priori estimates that are available on the Landau equation, and certainly the only one that seems promising somehow is the one that's related to the entropy. However, the entropy is a global quantity, and it's a good idea to look, to use the entropy to try to control truncations of the solutions. So this is done in the following way. Right, so we're going to look at quantities like f minus kappa plus, which I'm going to denote as f kappa plus, right? And so log plus of z, which is the max of log z of 0, right? And so you introduce this truncated entropy generating function, h kappa plus of g, which is scaled in this way with respect to kappa. So it's kappa h plus of g over kappa. Right, so essentially use the idea that the log at infinity is homogeneous to degree 0 if you want, right? So and h plus is this function, is z log plus of z minus 1 plus. So in other words, it's z log z minus 1, where z is larger than 1. Okay, so here's the graph of this function, and so this function is going to select those places where g is larger than kappa. Okay. So now what can you do with this? So you can prove that if you take Villani solutions of this Landau-Coulomb equation, I don't know if it's true of any H solution, but it's certainly true if you construct your solution by the process of Villani, then you can write the the H theorem here. With a test function, say a smooth test function in time and velocity. And what you find is that the truncated entropy at time t2 is less or equal to the truncated entropy at time t1. So this is localized in some by this psi here. So phi is psi squared, right? So you have the time, of course, you have the time evolution of the test function, so that's not a big deal. And you have a term, so this one here involves the dissipation, okay? And this other term is the defect of this truncation to be exactly dissipated by the collision process. Of course, I mean, this dissipation term is caused by the symmetries of the inside the collision integral, and these symmetries are destroyed if you just start truncating the distribution function at some places, right? It's no longer satisfied. Okay, good. So, but what you end up is the combination of these two terms, the one that includes the normal dissipation term and plus additional terms, which hopefully are going to be manageable, right? Okay, so here little phi is mod psi squared, psi squared, and A is the diffusion matrix. Okay. All right. So this holds true, say, except maybe for T1 and T2 in some negligible Lebesgue negligible set of times, but it doesn't matter because in the end we're going to average in T2, so it's not a big deal. Okay. So now, if obviously you can try to use it to localize this in balls or in balls for these integrals in fixed times, and in parabolic cylinders if you integrate also in time. And so if you assume that your initial data has mass controlled by two numbers, little m naught and capital M naught, has bounded energy and bounded entropy, then from this previous identity or inequality, whatever that was, right? So you can write a constant that depends exactly on those parameters, m naught, capital M naught, so the bounds on the mass, the bound on the energy, the bound on the entropy, that depends on v naught, the place where you center your parabolic cylinder, and so you have the truncated entropy evaluated in your parabolic cylinder. So here you take a soup norm in time and you integrate this quantity in velocity, plus the Dirichlet term and the Fisher information in the parabolic cylinder. So here you don't have this unpleasant 1 over v to the cube weight because you localize in velocity, right? So you don't have to worry about that. That of course appears, that explains where you have a v naught dependence in the constant. So that is going to be bounded by terms which take into account the interaction of the truncation and the collision process. And these terms are written there, so they're a bit unpleasant. I'm not going to, I mean, this computation is not to be done in public, as you can imagine. It requires some privacy. Voila. Okay, so that's essentially, so you know, I could say something like this is the property of the solution which we're going to use. Could define the notion of solution that would be solution satisfying this. But in reality, what we do is we take the same process that was used by Villani to construct H solutions. They happen to satisfy this property here, and that's all you need. Okay? Good. So now let me return to, so I already mentioned the similarity between the Navier-Stokes equation and Landau equation. There is, however, a difference, a rather serious difference, which is about the scalings, right? So the Navier-Stokes equation has a scaling which is well known. So you take U as a solution. Then you have epsilon U of epsilon squared T and epsilon X, which is also a solution. So here you have a richer family of scalings. In other words, you have a two-parameter family of scalings, right? So if F, T, and V is a solution, lambda F, lambda T, and mu V is a solution. Mu and lambda are not connected whatsoever, right? I mean, they're totally independent. Well, you can see that obviously on the isotropic, it's obvious on the isotropic Landau equation, and it behaves in the same way for the real Landau equation. Okay, so now if you look at how this scaling acts on the truncated entropy and on the dissipation term, which are anyway the left side of this inequality here. Well, so this scales like lambda divided by mu to the cube, and this like 1 over mu. And because you want these two terms to behave in the same way when you zoom, then this tells you that you should choose, say, lambda equals to mu squared. So you choose mu equals epsilon and lambda equals epsilon squared, right? And so really you're back to the same scaling as in Navier-Stokes, right? Because F is going to be to scale like epsilon squared, F of epsilon squared T and epsilon V. So this extra freedom, if you want to keep both terms the same size on the left-hand side in inequality, disappears, and you're back to the same family of scaling as for Navier-Stokes. Good. Well, good, I don't know. I mean, at least that's what comes out. Okay, so now the idea is to zoom near a point. Say you pick your favorite T0, V0 in the space-time domain. Well, space, velocity, and time domain. And you zoom near T0 and V0 in this way by some epsilon, which is a small, epsilon is going to converge to 0. And you observe that there's already a critical quantity in the sense that if you look at F epsilon convoluted with the Gaussian, with the Coulomb potential, so F epsilon convoluted with 1 over Z, right, 1 over normal Z, which is the quantity that appears in the diffusion matrix. Well, this turns out to be critical for the L infinity bound in the sense that if you compute the L infinity norm of this convolution in some parabolic cylinder, it's independent of the zooming parameter F epsilon, right? So the L infinity bound is the same here and there, right? So you don't gain, you don't lose anything by zooming in on this quantity. Good. So now then you're going to take this estimate, which I showed you before, and you scale it. So you scale in a following manner. So F scale like epsilon squared. So the level at which you observe F should also scale like epsilon squared. So the enlargement of the cylinder is going to scale like 1 over epsilon. Also the radius of the ball, or the size of the cylinder itself is going to scale like 1 over epsilon. And then you are going to look at your F epsilon, your rescaled Villani solution, minus kappa epsilon plus F epsilon plus kappa epsilon. Okay? Good. So then you scale this inequality which I showed you before in the key inequality, and you end up with an inequality of this form. So you have here the truncated entropy after rescaling, right? So which is measured in the cylinder in soup norm in T and in L1 in the ball. It's integrated in the ball. Then you have the Fisher information in the parabolic cylinder, and you have these extra terms here. So, but if you look at these extra terms, of course they're nonlinear, but the nonlinearity which you have is smaller than what appears from here and there, because here, yeah, I mean, you might say, wait a minute, so here you have an f epsilon log of f epsilon squared, but it's integrated in time. Whereas here you just have f log of f, but it's a soup norm in time. And here I remind you that you have some extra, Sobolev control that's going to help you with this, right? So you want to say that, you want to think that this term really is not, it's going to be in some sense not wild compared to the things which are on the left-hand side. Okay, that's the hope at least. It's a sort of depleted or tamed nonlinearity. Okay, good. Then with this, one way to look at the problem is to apply some de Giorgi iterations to set up a local regularity criterion. So it goes on in this way, right? So you take your Scale-Villani solution of the Landau equation, and you assume that initially, the initial data, unscaled, right, has mass-controlled mass between two constants, little m naught and capital M naught, finite energy, finite entropy. And suppose that you have a soup control on the f epsilon convoluted with the collision kernel. Actually, you just want to look at the tail of the tail of Coulomb potential. I mean, assume that you have a control by some z epsilon, so say z epsilon larger than 1, but you have a control like this, right? Then if this quantity, so if you look at this quantity here, so you have the dissipation term you have the truncated dissipation term that comes from the de Villette theorem, that's the Fisher information, whatever you want to call it. And here you replace, if you want, the truncated entropy by f epsilon minus 1 plus. It's smaller, but it's enough to control that. So if you control these two quantities by something eta divided by z epsilon to the 3/2, with eta small enough, so there is this eta, such that if you have this, then you can use the de Giorgi iteration to prove that f epsilon is going to be less than or equal to 2 almost everywhere on a smaller parabolic cylinder. So here you have a parabolic cylinder, say, of size 2. At the end of the iteration, you have a parabolic cylinder of size 1/2. And if you have this, if you return to the definition here, it tells you that f is going to be bounded on a smaller cylinder. Okay, so that's the criterion which we are going to use for regularity. Okay, so then let's look at the axisymmetric case. So now there are two ingredients, there are two things which you can prove. The first one is that if you're away from the axis of symmetry, then everything behaves like you're in 2 dimensions, really, because axisymmetric, you lose one variable. So things are going to be nicer in terms of Sobolev injections and so on, Sobolev embeddings and so on, and therefore you can control your f in the new variables, in the axisymmetric variables, in some parabolic cylinder, but of course it's a parabolic cylinder in the cylindrical coordinates. You can control that by something which is going to be L1 in the ball. So these quantities are perfectly okay, right? I mean, this is anyway in L infinity, but you just integrate it, so that's fine in time. And the quantity which is here, which is also controlled, right? Because it's square root of f times the gradient of square root of f, and both are known to be L2. Okay, so that you have a control of this form here, and another thing which is a little more touchy, which involves more careful computation, is the fact that this critical quantity in L infinity is also controlled in that case, right? So you can prove that the diffusion, essentially it's F epsilon convoluted with the Coulomb potential. It's bounded by the initial entropy plus something that's like the distance from the distance to the axis of symmetry, right? So this rho naught is the distance of the point at which you're looking to the axis of symmetry. So it appears, of course, in the estimate which is here. But with this, once you have these two lemma b and lemma c, lemma a and b, once you have these two controls, then you return to the de Giorgi criterion to prove local regularity. And well, I mean, you have to control this quantity here, right? I mean, you have to control the truncated entropy, say at level 1/2, plus the dissipation term, say in some parabolic cylinder, say of size 2. And you can show that this is controlled by the z star. So where is the z star? Is this quantity here, which is this critical bound, right? Times the L2 norm of f in the parabolic cylinder. But here, because you have this, because f in this parabolic cylinder, because it depends on the, because it's axisymmetric, then you can actually compute exactly what it is. Because of the zooming, then it's the integral of the capital F squared, but on a set of vanishing measure. So this goes to 0 as epsilon tends to 0, and so for epsilon small enough, this the right-hand side of this inequality is going to be small enough, so small that it's going to go below the de Giorgi threshold, and then you have a bound by the de Giorgi iteration. Okay. So that's essentially how this works. So yeah, I mean, to conclude, yeah, I mean, the message is that axisymmetric or radially symmetric Villani solutions of the space homogeneous Landau in space dimension 3 are going to be regular away from the axis of symmetry or from the origin in the case of radial solutions. So I mean, this proof is based on the Giorgi method, but I'm sure there can be another packaging of this proof. I mean, it's just like Alexi and I mean, I think we all like the de Giorgi iteration method. Alexi and Cyril and myself. It's a beautiful idea. One key ingredient of the proof is this upper bound for the diffusion matrix. So this lemma b, which I showed you, as you can imagine. Then. There's another thing that you can do, but I don't want to insist so much on that because I'm not quite sure that the result is optimal as it is. If you use the same approach but with some additional ingredients, so you need to control the local mass, then you can show some partial regularity result, which we're not very satisfied with this. So in other words, if you look at the parabolic Hausdorff measure of dimension 7/2 in space-time, I mean velocity and time. So because it's parabolic, it's not as bad as it looks, right? It's saying we're in the space of dimension 4. You might say 7/2 compared to 4. You don't gain much, but in reality, its parabolic dimension would be 5, not. Well, it's not great. So this parabolic Hausdorff measure of dimension 7/2 is equal to 0 for the set of t's and v's around which f is not going to be L infinity, right? So that's in the Coulomb case, which is the case of interest in physics. Now, of course, mathematicians have generalized so that it becomes trivial, you know. I mean, that's a Grothendieck principle. Oops, I shouldn't say that, but yeah, I mean, there's a range of potentials. where A of Z is Z to the 2 plus gamma times this orthogonal projection, with gamma between -3 and -2. This is called the very soft potentials. I don't think they're physical. I mean, the only one that's really physical, it's the Coulomb potential. But in that case, of course, the Hausdorff dimension improves, right? I mean, it's to the point that if gamma is close enough to 2, I don't remember, this partial regularity would imply regularity of axisymmetric solution, exactly as in the Kohn-Caffarelli-Nirenberg. Okay, very good. So what else do I have to say? Oh, that's the most important message. Yeah, happy birthday. Best wishes for the future.
Thank you. There are some questions. Maybe the George is cool.
So, if you have the epsilon regularity theorem and all these analogies in the estimates with Navier-Stokes,
Yes.
why are you getting 7/2 and not 5/3,
Good question.
like, you know, in the Sheffers?
Yeah, no, that's
What are you losing in that exponent?
well.
All right. So there are similarities with Navier-Stokes. There are, however, some serious differences. Of course, you might say that anyway, the Caffarelli-Nirenberg doesn't use fully the structure of the Navier-Stokes equation, right? But it used to some extent, and you could say, after all, what we use is maybe in the same equivalence class of what they use. Here, however, the non-local quantity, which is analogous to the pressure, is a diffusion matrix. So in their case, this non-local quantity is a source term. Here, it's a coefficient, and it's not handled in the same way. I mean, this is, in the treatment of this term, this is probably something where we lose a bit, okay? Yeah, perhaps also, maybe I shouldn't say this, perhaps also that has to do with the De Giorgi packaging. I'm sorry for saying this. Maybe using the original procedure, this sort of renormalization technique.
The smallness, you mean?
Yeah.
That's actually
But
a minimum surface type argument. So you can even credit that to De Giorgi if you want.
Well, I'm sure. I will be glad, actually. Yes.
I mean, it's a blow-up argument, actually. So Scheffer is a student of Albert. He got it from that crap.
So you're not angry at me was my answer. Okay, very good. So I'm glad. Yeah. Well, I mean, at the end of the day, yeah, this is it. I mean, this is the treatment of this. It's the difference of the treatment of the pressure and the diffusion matrix, which probably is a problem.
So it's like a linearization type argument, like the one with the rescaling might actually give you something better.
Yes. I mean, it's certainly something that we have to look in more detail. Yes.
Yeah.
There's a question.
Yes. So, what people think? Blue?
Well, so there is in writing, but it's already quite old. In writing, maybe in the last month of last century, there's a paper of Cédric, saying that he believed at the beginning that it would be blow up in finite time. And now he's not so sure that it's going to be blow up because numerical simulations don't show. Well, let me come to this because numerical solutions don't show blow up. So the people doing numerics, what they believe, at least in the case of radial solutions, right? I mean, already we'll be very happy with this. So what they believe is this: suppose that you have an initial radial profile. Okay, which is not necessarily decreasing in V. It's not necessarily. Okay, so there's a first phase of the evolution where it will rearrange so as to be monotonic, right? Because I mean, you go to a Gaussian in the end, so I mean, it will rearrange in a way that it's going to be monotonic at some point, and then once it's monotonic, no blow up. But okay, right? I mean, this is, as you say, it's a numerical simulation. It's very hard, because when you, I mean, there's a little problem. You see, when you look at the radial equation, Okay, maybe I write this on the board for you, right? So the radial equation, suppose that f is a solution of Landau, and suppose that f of t and v is in fact a function capital F of t, and I'm going to use norm of v squared. So the fact that f is a solution of Landau so is equivalent to the fact that capital F is a solution of the following equation here. So I think it's 2/3. 1 over square root of capital V. So I'm going to call this variable capital V, right? The mod V squared. So you have d capital V of the integral, so 0 to infinity. And here you have an interesting term, which is V inf W to the 3/2, okay? Times F of T W dVF minus F of TV dWF, and you integrate dW, and this is the Landau equation in radial variables. Now, if you look at this equation here, you see immediately that for V equal to 0, then the diffusion term, which is this integral here, bites the dust, disappears. It's equal to 0. So you lose the diffusion exactly where you would like to.
Where you need it.
Yeah, so it's yeah, it's hard to say. Okay.
Okay, thanks for this answer and for the whole talk. Thanks again.